We're now going to derive an expression for the power in an electric circuit. We're going to start with the definition of power, work per unit time. In the last unit, we found out that work is equal to the charge times the voltage, QV. We will take this QV, put it into the work up here, and we now have power is QV over T. Let's look at this line right here. And again, this makes mathematicians a little queasy, but we're going to do it anyway. Q over T is just charge. Actually, it's delta Q per delta T, but for purposes of this, we'll just take a little shortcut here. We now have I is equal to Q over T. It goes in here, and I will have power equals IV, current times voltage. Looking at this, what do you think happens if the current is increased? What would happen to power? What would happen if the voltage is decreased? Discuss that with your groups or think about it yourself. Let's go back to the water analogy to try and think about electrical power. Water at the top here, we have water flowing down a flume, hitting a paddle wheel, and it spins it. The water up here has gravitational potential energy and kinetic energy. As it falls, it loses gravitational potential energy and the wheel gets turned doing work. When the water falls to the bottom, it is now slower having done work. If the wheel weren't here, of course, the water would fall and speed up as it gets to the bottom. It's basically a falling object. But a lot of that energy is chewed up in spinning this wheel. It has done work on the wheel. Electric circuits are similar, again, as an analogy. A charge will fall, let's say this was charge and this was a circuit, a charge will fall from a high voltage to a low voltage, and in the process of falling, that energy is transferred into lighting up a light bulb, running a motor. So as it's doing this work, it's using power because it's using work per unit time. So if this wheel were spinning quicker, you would imagine that would be more power. There would be more work delivered in a shorter period of time. So that's the analogy here. Let's go back to power. And what is the unit of power? Since we started with the same definition of power that was used in mechanics and derived the power expression for circuits, here we have power is work per unit time. And we found out that power is current times voltage. Work is measured in joules. Time is measured in seconds. So the unit of power is joules per second. And in honor of James Watt, who made critical contributions in developing efficient steam engines, the unit of power is known as a watt. Basically, we're using the same units for electrical power as mechanical power. Let's come up with some other expressions for power. We're going to start with power equals IV, and we're going to fit Ohm's law into power. So first what we're going to do is replace the I here. I is V over R. So you put that, substitute that into here. We get power is VV over R. So power is equal to V squared over R. Is there another way to write power? Well, of course, or we wouldn't have asked. We can say I is V over R, this is Ohm's law, can also be written as V equals IR. This time, plug that in to the power equation, and we have power equals I times IR, or power equals I squared over R. All three equations are equivalent, and it just depends on what you're given as to what equation you'll use to get a solution.